Nice to see you available Sunday evening. But of course, as always, before we start, I need to remind that it's friendly and inclusive space. So let's encourage each other without any negative comments. Please maintain a professional and friendly attitude. This session will be recorded. If you have anything to tell about this community, don't worry, and anytime contact me via email. So, Ines, I start.
Hi.
I stop sharing. So yes, you can start sharing. Biggest
Okay,
thanks
then.
for joining this week 4. I think yes, it's week 4 dynamic programming today.
Yeah, it's already a month. Can you believe since we started? Yeah. Then I will start sharing my screen.
Okay, you're welcome. And this session will be recorded and shared later on our YouTube channel, LinkedIn, Meetup, everywhere.
Very nice. Well, then I guess let's start. Hey everyone, thanks again for coming. It's been a month since we started. Crazy how time passes by so fast. So I hope you're all doing great. Let's start. As usual, we will start by recalling what we have seen last week. We explored graphs, and we saw how it all started with Leonhard Euler when he was trying to solve the Königsberg Bridge problem. And then we have seen the most famous traversal algorithms, which are basically BFS and DFS, and we have together seen what are the different logic behind them, the runtime, and the data structure that is used. Now, today we will build on that knowledge and we will dive into the mindset of dynamic programming. But first of all, why do we need dynamic programming in the first place? Well, it's because recursion was extremely messy before dynamic programming. And how exactly was that? Well, in order to try to answer on this question, we will try together to analyze one of the most recursive, most famous recursive functions, which is the Fibonacci sequence. Well, we all know Fibonacci, and we all know also this the golden ratio that is used behind the sequence as well. So the sequence is defined by this recurrence relation, and basically we have two base cases. When the n is 0, then it's 1, and when the n is 1 as well, we return 1, and then we just recursively call f of n minus 1 plus f of n minus 2 in order to calculate the nth Fibonacci number, sorry. And let's start by visualizing how the sequence would look like, for example, for Fibonacci 5. So in order to visualize Fibonacci 5, it gave us this call stack as a tree. But wait, what is exactly a tree and how do we construct it? Oh yeah, or maybe you are asking also other questions. For example, what is a stack tree, and is a tree a new data structure, or how did we obtain this tree in the first place? Well, if we go to revisit last week's work, we will see that I will first answer the question, is a tree a new data structure? It's not, because last week we explored the graphs, and a tree is basically nothing but a simple and directed graph, but with a slight difference. In a graphs, we have neighborhood relationship between the nodes, but actually in a tree, we just have a parent-child relationship. For example, this node is a parent node for this, and this one, and so on and so forth. So a tree is basically a special type of a graph. Now, how do we visualize the Fibonacci recursion as a tree? Basically, each Fibonacci number depends on the two previous terms. So this means that every number calls its two predecessors, forming a branching structure. And at the end of the recursive process, we get a tree where the leaves correspond to the base case, actually, which are f of 0 and f of 1, and they are both returning 1. And now, what does the post order mean? Because here we have seen that the Fibonacci recursion follows a DFS traversal algorithm, which we also covered last week, but which is also a kind of post order traversal. Well, a post order traversal is basically just computing nodes with the leftmost node. For example, we each time visit the leftmost until we reach the base case, and then we backtrack and then go right, and then we in the right branch we also follow a leftmost logic. And then we finally have the computed nodes in the desired order. And this kind of traversal, we call it post-order traversal because it first visits the left node, then the right node, then computes the parent node. And now, if we simulate these steps into our Fibonacci number Fib5, we will have this thing. As we want to calculate the fifth Fibonacci number, we call Fib5. We push it onto the stack. This is our call stack here. So after pushing it onto the stack, we check if Fib5 is a base case. So is 5 a 0 or 1? It's not. Then we just call its predecessors, which are Fib4 and Fib3. Then which branch to take? Simply, we take the leftmost branch. So in this case, it's the Fib4. And it's actually our first recursive call. So after calling Fib4, we push it onto the stack. So we have here Fib5 and Fib4 on top of it. Then we check, is Fib4 a base case? It's not. So as usual, we call its two predecessors, which are Fib3 and Fib2. And just like that, we always take the leftmost branch, which is in this case Fib3, so we push it also onto the stack. So now we have Fib5, Fib4, and Fib3 on top of each other. Is Fib3 a base case? It's not, so we recompute. We call Fib2 and Fib1. Since Fib2 is the leftmost branch, then we push it also onto the stack here. We check, is it a base case? Sadly, it's not. So we have to call. We have to take a recursive call for the first time, and then we will have Fib1. So we push it onto the stack, and we check, is Fib1 a base case? And in this case, yes, it is indeed. So we simply pop it from the stack and save its value. So it's 1. And the logic says that we should take the leftmost branch, but if we observe our Fib1, it's a leaf, so it's the last node in our in this branch. So we just backtrack to Fib2 and check if it has right branches. And in this case, yes, it has. It's Fib0. So we push Fib0 onto the stack and we check, is it a base case? Yes, it is indeed. So we pop it and we store its value. Now we check if the Fib0 has left branches or right branches. In this case, it's also a leaf. So we backtrack and go to the parent. And just like that, I know that I'm done with computing all the branches that belong to all the children that belong to this node. So simply, I also pop the Fib2 and calculate it, which is Fib1 plus Fib0, which is in this case 1. And I'm done with calculating fib2, so I backtrack to its parent node, and then I check if there are any right branches. Yes, indeed, there are some right branches, which is fib1. I push it onto the stack, and then, I push it onto the stack, and then I pop it and keep computing all the nodes till the whole tree is traversed. Now, let's try to implement this logical steps that we just visualized into a code. As usual, I wrote it in a Python code. So, in order to make you feel integrated into writing the code, although it's a really simple one, the recursive function is defined as follow. We define our base cases, which are f of 0 and f of 1. If our n is none of these numbers, then we just recursively call or return f of n minus 1 plus f of n minus 2. And if we put that nicely together into the Python programming language, we will have this code. We will call the Fibonacci n. If n is 0 or if 1, then we just return n. And then if it's not a base case, then we just return the recursive calls of Fibonacci n minus 1 and Fibonacci n minus 2. Now, as usual, we always want to write efficient code. So let's check the efficiency of this recursive algorithm. Basically, each node calls recursively two of its predecessors, and this branching into two nodes goes on and on till we reach the base cases. And at its most, the depth of this tree will be 5, which is actually the number we called initially in our function. And then, as said, each node has two recursive calls, so the total amount of node that we can have at maximum would be 2 at the power of the height. So it's 2 at the power of 5, which is an exponential growth, and it's really, really slow. So basically, we just kept using this recursive function for years until Richard Bellman came to rescue us from the amount of time that's wasted on the exponential time complexity. Well, let's make recursion great again. Well, Richard Bellman, or simply Bellman, was working for the US government, specifically in the military research, when he introduced dynamic programming philosophy. His goal was to optimize problems by breaking them into smaller subproblems and storing already computed results to avoid redundant calculations. And that's exactly what dynamic programming is about. It's about optimizing recursion by avoiding repeated work. And dynamic programming, what does it mean? Dynamic refers to how decisions evolve over time. And programming is actually a term for optimization in maths. Yeah, so dynamic programming is just ordering your computations in a way that avoids recalculating duplicate work. Or if we put it in other words, it is a technique used to avoid computing multiple times the same subproblem in a recursive algorithm. Many think that dynamic programming is a new algorithm of solving things. For example, we said for traversal algorithms, we have seen BFS and DFS. So it's just an algorithm that we use, but it's not a ready algorithm, but it's just a technique, or let's say a philosophy how to approach a problem and how to solve it. Now, key points about dynamic programming. First is optimal substructure. The problem can be solved by solving smaller subproblems. I have a big problem, so I divide it into smaller problems so that resolving those smaller problems will be much easier than just observing the whole the problem as a whole. Yeah, and then we have the overlapping subproblem term, which means that subproblem repeat, so also their solutions can be reused. Yeah. Now, the dynamic programmer's first applications were as said since Bellman was working for the US government. One of the first approaches or applications, sorry, it was used in missile trajectory optimization, so for rocket trajectory, and it was also used for resource allocation as well. Now, where does dynamic programming is worked nowadays behind the scenes? One of the very useful use cases are AI and machine learning. For example, the reinforcement learning through the Bellman equation. Also in bioinformatics, when it's used for the DNA sequence alignment, and also in finance for portfolio optimization. And last but not least, it's highly used in coding interviews for so when you're applying for a job or an internship or whatever, dynamic programming is a love problem or algorithm to implement in those coding interviews. Now, back to the thing. How does dynamic programming turn our exponential growth into a linear one? Basically, as said, since we have overlapping subproblems and their solutions can be reused, we will try to implement that for our Fibonacci. Let's revisit the tree that we had. And if we observe it, we will see that, for example, this whole subtree or subproblem is also seen here. Well, this one is seen before the right one. So yeah, and if we dive even into the break this subtree into smaller subtrees and smaller subproblems, we will see that, for example, the fib2 is called here, here, and here. So there are three calls for fib2, and if we even break the problem of calculating fib2 into smaller ones, we will see that fib1 and fib0 are actually called many times, so there is a lot of redundancy. And yeah, these arguments, I've seen them before. So that's why we will see these two techniques in dynamic programming, which is memoization and tabulation. We will start first with memoization. Yeah, it's basically a top-down approach, and it's just being lazy and saying, okay, why recompute when you can just recall? Yeah, just think lazy but smart, solve problems only when needed, and memorize answers. And this memoization approach uses recursion plus caching to store already computed results. And if we implement this logic for our Fibonacci, we will have recursion plus memoization. We will have a new, you can call it a set, or some people also use hash maps or the dictionaries. So you check if the n already exists in our set or dictionary, then we just return the value. No need to make any further computations or calls. Then if it's not, like perhaps our n is a base case, then we just return the n. If it's neither of those cases, then we just call the Fibonacci n-1 and n-2 as usual, but just with a small addition that we add the dictionary that we have or the hash map into it, and we store the result in our hash map memo. And at the end, we return the memo of n. Now, how efficient is memoization? Well, it's time complexity. Basically, we compute each value just once, and then we reuse its computation or its value. So at the end, we just have big O of n. And for space complexity, we use recursion, which is for a stack plus a cache. So it's also big O of n, since we just push at max n elements onto the stack. And for the cache or our memo dictionary, we also will add or append at max n elements. Now, we had at first a slow algorithm that works exponentially, and then just through dynamic programming, which is basically solving the problem but with a different approach, we had a much faster algorithm, which is a linear one. Now, why do we need another technique? Isn't memoization enough? Well, in order to answer this question, I have prepared this Jupyter notebook. This is the Fibonacci as a recursive solution. So for example, let's start by computing this. If we run fib5, in no time we will get its value, and it's 8, so it just needed 0 seconds. Yeah, I said CPU runtime isn't really an accurate time complexity analyzer, but just in the sake of seeing why we need another method other than memoization, we will take CPU time this time into consideration. And then if I check fib 20 with the recursive call, also in no time it gives me its value. But for example, if I check fib 40, it will take much longer, and I don't know how much exactly. I will just wait patiently. Okay, this is much longer than I expected. I think because there are many tasks that are running through my CPU right now. The whole microphone recording and the camera as well. Well, I'm not gonna wait for that. It's already I don't know how many seconds. I'm just gonna stop it. So, oh yeah, okay, yeah, it has the value. It took 27 seconds, and yeah, the fib 40 is this one. So you see how much time it takes. It's just really annoying, and this is just fib 40. Imagine I want to calculate fib 100 or 1000 or other bigger numbers. So this is the Fibonacci with the memoization methods, and let's just check the same examples that we've seen here. Then fib5, just in no time it gave me its results. fib35, also in no time I have the result. Now let's see if I call fib100, will that would be also efficient and fast? Yes, indeed, it just in no time it gave me its number. But for example, if I check for 5000, well, in this case, yeah, we will have recursion error. And basically, it says recursion error, maximum recursion depth exceeded. So since in memoization we are using recursion, which uses a stack and the memo dictionary, we have the problem of a stack overflow and reaching the maximum recursion depth. And this is very problematic because I want to write code that works for, I want it to be dynamic. I want it to work for any big ends. And that's why memoization isn't really enough. And if we go back to our presentation, we will now introduce tabulation. So memoization is a top-down approach. Tabulation is a bottom-up approach. So it says, let's just solve everything in advance so we never have to think again. And it basically uses an array to store results iteratively, and it avoids recursion. So now we are safe that we will not have the same error of reaching the maximum recursion depth. And it uses less memory since we won't need the stack. So yeah, let's check its implementation in Python. And it basically looks like this. I call the fib_tab_n. This time, no need to have any extra arguments. And then I just initialize my array. as zeros at first, then I put dp of 1 as 1, and then just iteratively with a for loop, I go through all the indices in my array and update them one by one by computing dp of e and set it as at its predecessors, and then just return the dp of n, which is really intuitive and really, really simple, just using a for loop. And how efficient is tabulation? Well, each value is computed once. So we have an array, and we will go through the array index by index. So it's big O of n. If I'm calling fib of 5, then it's big O of 5, and so on and so forth. And the array will have the same size. So the space complexity, which is about the array dp, is also big O of n. Yeah. So when it comes to efficiency, tabulation and memoization work hand by hand, and they agreed on working with big O of n. And in order to convince you and bring the proof, we will see its CPU runtime. So this is the same algorithm I included in the slides. And yeah, fib bottom up, we call n, then check if it's a base case or not, then no need to... oh yeah, this is actually a more efficient one since I wrote it after including the one in the slides. So yeah, if it's a base case, then no need to use any extra memory or any for loops or whatever. So we just return the value. Then we initialize our array with zeros, or in this case with none. It's the same basically. It depends on the programming language you're using. Yeah, and then we initialize the first indices in our bottom-up array or our DP array. Then just with a for loop, we go iteratively and fill or update the value of db of e, and then just return the last value, which is the last index or the last case in our array. So in the memoization, we were stuck with the 5,000 term. So let's just check it, how it works with the tabulation. Let's just run this one and then check it. Yeah, imagine how fast this is. Just in 0.0 seconds, it gave me the whole term, which is a very, very, very long number. Anyway, yeah, and then if I go even further and check, for example, 10K, how much that is, yeah, simply it gives me in no time as well this very, 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 very long number. So tabulation works very nice when it comes to big numbers and when it comes to high recursion depth. Yeah, to summarize the difference between those best friends, yeah, memoization uses recursion plus cache, and tabulation just uses an iterative array or simply an array. Yeah, memoization is a top-down method, and tabulation is a bottom-up method. So we start from the base case and we build on it. And in the memoization, we start with the f of n and then try to recursively call its predecessors. Yeah. And then when it comes to time complexity, they both work in big O of n, linear time. And when it comes to space complexity, the memoization takes big O of n since it has a stack and the memo cache. And tabulation also needs big O of n, linear space, but it can be optimized, so we can get big O of 1, so it's constant amount of time. Yeah, and the best use cases for memoization, it's basically for recursive problems, but with a low recursive depth. That's the only limitation that we have. Otherwise, we will get a Stack Overflow problem or error. And for tabulation, it's we can use it also in the recursive problems, but it's basically used for the sequential problems. Yeah, What are a common algorithms that are using dynamic programming, or we can use DP in it? Well, first of all, the Bellman-Ford shortest path. Last week we discussed traversal algorithms for graphs, and we have seen that if we have a weighted graph, so BFS won't be really helpful for giving us the shortest path. So BFS gives the shortest path, but it will ignore the weights. And if I want to find the shortest path with respecting the weights, then the Bellman-Ford is the one that is the best used algorithm to solve this problem. Second, for example, we have the edit distance, which measures how similar or different two strings are. And it is essential for applications, just like the Google's Did You Mean? For example, if you Google something, for example, we will say, let's say you Googled Euler, and then, for example, did you mean Leonard Euler? This feature of Google uses dynamic programming, which we call edit distance. And as also a fun use case, I found the knapsack problem, which determines the maximum value of items that can be carried in a knapsack with fixed capacity. And if I want to put this in other words, let's say we have a list of items with weight and value, and you have a knapsack with a maximum weight, for example, let's say 60 kilo. So you want to put all the as max, or not really as max. You want to put the items that have the highest value with the lowest weight. Yeah, this is a well put in together. Yeah, and also, you can use dynamic programming to check the longest palindromic subsequence, which is finding the longest subsequence within a streak that is also a palindrome. A palindrome is a string that's the same read from the left as the right side. So if we reverse the string, then it's the same as the original one. Yeah. And before checking what's next, also one of the very good platforms that I invite you to check. Maybe you have heard of it as well. It's LeetCode. Well, there are many dynamic programming challenges or problems in LeetCode. So just check them. You will find also these algorithms that I mentioned there, and just have fun with applying it. Yeah. Next, we will see greedy algorithms. Yeah, that was it for today's session. Thanks so much for paying attention. I hope this was helpful. And then, just like always, here code to connect with me, ask me questions, or just connect with me. Yeah. So I'm done. I will leave you to Anna. And if you have questions, it's your time to ask. It's now or never.
So I see we haven't any questions, and I'm super happy. It's my lovely top palindromes, and your examples, real life examples, amazing. And I'm lucky to have palindrome name, Anna.
Yeah.
So,
Yeah,
yes,
it is indeed. Yeah.
yes. Mostly
If it's not in capital case.
It's a pity, but
Yeah.
you can start my name from small letter. It's okay.
Exactly. Yeah.
Yeah, so
Yeah.
I'm honored that I have palindrome name. So, okay, and so it brings us to the end of today's session. Biggest thanks for your impressive talk with interesting examples, interesting explanations, and of course, useful for a lovely everywhere Python. So,
Yeah,
and
as always. Yeah.
and I'll share later on our YouTube channel. And of course, please don't forget to leave feedback because your opinion is crucial for us, and it helps us to improve and make future sessions even better. Once again, thank you for joining, and of course, see you next session, next Sunday. And
Yeah.
until then, learning, experimenting, and building with AI.
Yep.
So,
Then bye.
see
Have a
you
nice
next time.
evening. Wish me
Many
luck in my
thanks.
exams.
Oh, lucky. Good luck on your exams. Yes, it starts.
Thank you. Thank you so much.
I wish you best on your exams. But I'm sure you're cleverest of students,
Thank
so
you.
you should
Thank
pass.
you.
So I wish you best on your exams.
Yep.
So see you
Then
on next
ciao.
sessions. Ciao.